Okay, everybody. Howdy, howdy. Don't forget that I think I sent you all an email. I hope y'all got it. That I will actually be out of the office until about noon today because I gotta do some checking up on some teaching observations. Checking up doesn't sound very good. Let me remind you of the last theorem we had. And H K inside E inside F fields, and H is a subgroup, the Galois group of F over K. Then A, remember what this prime, this is sort of like operating on this group, and it turns this group into a field. This is the set of stuff in F, such that sigma V is V for all sigma and H. This is called fixed field of H, and it is the fixed field of H is an intermediate extension, and B, E prime now the prime operation works on a field and turns it into a group. This is the collection of all automorphisms of F that fix K, such that sigma of E is equal to E for all E and E. And this is a subgroup of the Galois group. We discussed this a bit last time. Let me point out, I'm going to put these remarks in because notice that 1 prime is equal to, well, of course, 1 is the group here. So 1 prime is a set of everything in F that is such that sigma V is V for all sigma in H, so for all 1, right? So obviously the identity automorphism fixes everything in F, no problem there. But the other extreme doesn't always work. Notice that that is not necessarily K. So a good example of this is if we have the extension Q inside Q root 2, we've seen that the Galois group right, because one of the pains that we went through last time is we showed that the only automorphism of this thing that fixes Q is in fact because of the fact that the cube root of 2 has to go to another root of x cubed minus 2, the only automorphism is the identity. And so if you look, so the fixed field is all of the big field. And in fact, when that happens and when that doesn't happen is very important, and it will be one of our equivalent definitions of what it means for an extension to be Galois. And so we'll jump to that right now. Definition. Let K and F be fields. We say F is Galois over K. If the fixed field if the fixed field of the group of automorphisms of F fixed K is precisely K. Here's another equivalent way to think about it, and it doesn't require really much thought to realize that it's equivalent, but it is a very useful observation. Equivalently, F is Galois over K if for all alpha there exists a sigma in Galois group over K such that sigma alpha. So in other words, it's Galois over K if given any element that's not in K, in F but not in K, there's something in the Galois group, there's some automorphism that actually moves it somewhere. So notice that this prevents alpha from being in a fixed field, and that's why it's equivalent to this. Let me make a remark, which is really kind of more of a spoiler remark, but I like to bring this up so that we can, so you can have something to kind of, a way to think about this. U is the root of some so let's look back at our simple extensions here. When is this Galois over K? So under what conditions is a simple extension where U is a root of some polynomial? Galois over K. If and only, and I'm not going to prove this yet, this is going to come up later. All roots, let's see, we'll say this is irreducible. Let me say that F of X is the minimal polynomial. So if and only if all roots of F of X are in so in other words, adjoining one root gets you all of them, and F separable. Okay. Now, what it means to be separable, we have not defined, and we will later. But basically, what it means to be Galois for the simple extension is when you adjoin a root of the irreducible polynomial, you magically get not just that root, but all the roots. For example, if you have a quadratic extension, this happens because all you need is plus or minus radical d. So this happens in quadratic, and it happens in other cases as well. Then F is Galois if and only if you get all the roots, and F is separable, which means that basically all the roots of F of X are distinct, right? So you don't have multiple roots from an irreducible polynomial. We'll talk more about that later. Okay. Any questions? So if you remember last time also, we had this, we looked at the following. Here alpha is the cube root of 2. Omega is -1 plus radical -3/2. If you remember, we had this diagram here last time of these intermediate fields of this extension. This is a degree 2, 3, and they corresponded to S3 E1, 2. Actually, let's see. Which is fixed by complex conjugation. This is about the E2, 3, E1, 2, E1, 3. We had a diagram that looked like this, and I may have confused the 1, 2, and 2, 3 because I forget how I set up my automorphisms work last time. And this is E1, 2, 3, 1, 3, 2. 3, this is 2, this is the index. 2. Remember last time when we worked through that long example, we got these corresponding diagrams. I am now going to state the fundamental theorem of Galois theory and kind of compare it to this here. Actually, this might be a 2-word. So the theorem (827) fundamental. Let's suppose that if K and F finite and Galois. So in other words, of course, that means we meant by our previous definition. K is the fixed field of the Galois group of F over K. And there's a 1-to-1 correspondence. There's 1-to-1 correspondence between set of intermediate fields of the extension between the fields that you can find between K and F and the set of subgroups of Galois. just like in this picture here, you can pair off intermediate fields of the extension with subgroups of the Galois group. And this correspondence is given by E. So your intermediate field goes to E prime. Remember, field against your group here, which is I've mentioned this before, but remember, what is E prime? E prime is the set of sigma in Galois group of F over K, such that sigma of E equals E for all E and E. So it's the set of everything that fixes E. Agree? And that's exactly what it needs to be, the Galois group of F over E, because these are the automorphisms of F that not only they fix K, they fix E. Right? So this is what it means. Galois group of F over E, that just means E is the fixed E. Such that, so this correspondence here, it's got a couple of properties. If L are intermediate extensions, then the degree of M over L so M is the bigger field is equal to right. Remember, these are the automorphisms that fix little field. These are the automorphisms that fix big field. And so this is actually a subgroup of this. It reverses the order, right? L is the little field in this big field. This is the automorphisms that fix little guy, right? There's less automorphisms that fix the big, right? And those degrees are the same. So in particular, Galois group of F over K, the order of this is equal to the degree of the extension. And two, if F is Galois over every intermediate field E, so if you've got an intermediate field, E is F is Galois over E, but E may not be Galois over K. It's Galois over K, if and only if the Galois group of F over E is normal enough, the Galois group. And of course, this means E prime is normal in K prime. Right, that's a translation there. And in this case, what happens when you have a normal subgroup, right? What happens in this case that E is Galois over K? That means this is normal, so I can quotient them out. And in this case, the Galois group Anybody want to take a guess here? I mean, after all, you can take, I can just be a bonehead and take any group that has a normal subgroup, pushing it out. This is actually Galois group. Anybody want to guess? In the case that, and of course, this makes sense because in this case, he is Galois over K. Notice that we can see this going on here, right? And you'll have to take me a little bit on faith here for a little bit of this, but we've already seen the schematic here, right? And here's the way this works. This is when prime it. What happens when I prime this field? Well, this is the fixed field of, or I'm sorry, let's see. Wait, I go. Right. So when I prime this, this should be the fixed field of Q alpha omega, which is actually the field prime should be the set of everything in the Galois group that fixes Q alpha omega, and that's just the identity, right? With this one, what happens to this prime? This should go to the subgroup of the Galois group that has everything that, these are all the automorphisms that fix this, right? And remember, this was, if you remember back to our example last time, this was the one that was subfield of the reals. The only automorphisms to fix that were the identity complex conjugation, which is what I call the 2-3 swap here. This was actually corresponds to complex conjugation. So our field, what's the step that fixes it? It's this. And same with it. I may have confused these two in the order. That's fine. What fixes, what's the stuff that fixes Q omega? If you look back at our table last time, it was precisely these three automorphisms. The identity of these other two were the ones that fixed omega. And what's the set of automorphisms that fixes Q? All of them. All of them fix Q, right? Everybody okay? Now there's also the statement here, F is Galois over every intermediate extension field P. So this is Galois over Q, because the fixed field, this is K. But if you look here, if you look at the automorphisms of this, that fix this, and you look at if you look at the fixed field of the automorphisms, it's precisely Q alpha. So you can verify for yourself that this is actually Galois over all of these. But it also says that an intermediate field is Galois over, in our case, Q, if and only if the Galois group, well, its corresponding Galois group of F over E is normal in the whole Galois group. These three are not Galois, right? Because they correspond to groups that are not normal, right? You guys know these groups are not normal in S3, right? And so, and we've actually seen that they're not Galois. This is not Galois over Q because this is not a normal subgroup of S3. And we've seen this as Galois because, for example, remember how we did earlier even in this class, if you look at Q adjoined with Q root 2, the only automorphism was the identity, and the fixed field is this, not this, which is what's needed for Galois. The fixed field of the automorphisms here is the whole field. Right? Same applies here. Here, these are not Galois. This one, however, corresponds to normal subgroup, one of index 2. This one is Galois, right? Because if you look at, or this one's Galois Q, because if you look at the automorphisms of this that fix Q, basically the only automorphisms of Q omega are the identity and complex conjugation, right? Because think of it this way. Here's an easy way to think of this. Omega is a root. I'm using the notation, but omega satisfies that, so it's a root of that quadratic polynomial. The only automorphisms of Q omega have to send omega to itself or the other root of this, which is its complex conjugate. Right? So there's two automorphisms of this thing right here. The identity and then the automorphism takes omega to omega bar. All right. Notice that that's still in there because so omega bar is -1 minus omega. And actually, you can just do the addition with that and see if that's true. If you change the sign of this and subtract 1 from it, you'll get its complex conjugate. So omega bar is still in here. That's an automorphism. The fixed field identity and the fixed field of both of these is in fact Q, so it is Galois here. So this little example that we did performed just like predicted in the theorem. Any questions? Does that help give you all the picture I hope? Any questions about the correspondence? Okay. Well, so let's start trying to prove some of this business. So as you might expect, we've got some lemmas along the way here, and start off here. And some of these lemmas are couched a little bit more generally than we need, but that's okay. Lemma. Here's the first one we need. Let K and F be Galois. Well, actually, let's do this. Okay, so suppose that L inside M are intermediate extensions. We'll assume that F is Galois over K, and we'll let G equals Galois over okay, so now I've got everything. L and M are intermediate extensions of this Galois extension. G is the Galois group, H and M are subgroups. We have the following. So hold this over here. A prime 1 and K prime equals G. Number 2, 1 prime equals F. C, if L is in M, then M prime is a subgroup of L prime. I'm not going to use group theory notation, so I won't confuse myself here. If H is an N, then M prime is an HN. So in other words, these primes reverse order of inclusion. Number E, L is contained in L double prime, and H is contained in H double prime. And F, L prime, L triple prime, and H prime is H triple prime. Okay, so let's look at this. F prime is the set of sigma in Galois group such that sigma V equals V for all V and F. So which elements of the Galois group fix everything in F, right? Right, because remember, every element, well, of course, notice every element of the Galois group fixes everything in K, but because this extension is Galois, there is this sigma in the Galois group such that sigma alpha. Oh, wow. That's from the fact that it's Galois. So what that means is if you have something that fixes everything in B, then it has to be the identity, right? Because there's something that moves everything that's outside of K. And K prime equals G by definition. Remember B, 1 prime equals F. Well, let me remind myself here. 1 prime is the set of V and F such that 1 of V equals V. So 1 prime equals F because this works for everything. Okay, so now let's get to the stuff that's a little bit more interesting. We want to prove the containment reversing business. C. Let sigma be in M prime, which is the set of sigma in the Galois group. Such that sigma M equals M for all M. Note that L is contained in M, so sigma of L is equal to L for all L. Right, the fact that L is a subfield. Therefore, sigma is in L prime. So we have the M prime is contained in L prime. Okay, got that one. I think we'll find the next one similar for the containment of groups. D, let's suppose that H is contained in N. Now let field, but V be an M prime. And M prime is the set of V and F such that sigma of V equals to all sigma in M prime. And of course, M prime is contained right. Now, what I need to do is I need to show that it's actually in that V is actually in H prime.
You said that V is an element of N prime and you define N prime. You said sigma is an element of N prime. Are these different N primes, or is that not supposed to be?
Maybe I didn't mess myself up here. Let's see. V is in N prime, so it should be an element field. So something in F such that sigma V is V for everything in. No, that's right. For all sigma in N prime. N prime is a subset of the. Oh, I'm sorry. N. There we go. I put the prime on there for no reason. There. Okay. That better. Okay. And notice that, so what we need to do is show that V is in H prime, right? Well, since H is a subgroup of N, sigma V equals V for all sigma in H. Therefore, V. Right, because V is fixed by every automorphism of N, and so since H is contained in N, it has to be fixed by every automorphism of H. Okay, so. Okay. So let's do E. We want to show that L is contained in L double prime, right? Well, so to this end, note that L prime is the set of sigma in G if you got one group, such that sigma L equals L for all L and L. So now that we've made, let me record L double prime. Now notice, of course, this is a group. And so L double prime is back to being a field. And it is the set of L and F such that sigma L is L for all sigma in L prime. So if L is in L, then sigma L is equal to L for all sigma in L prime. Therefore, L is in L double prime. So, in particular, L is in L double prime. Everybody okay with it? And let's do this one too. H prime is sigma in V, or it should be V in F such that sigma V equals V for all sigma in H. And H double prime is the set of sigma in the Galois group such that sigma V equals V for all V and H prime. So if sigma is in H, then sigma of V equals V for all, right? So sigma is in H, and sigma of V equals V. Then sigma of V equals V for all V and H prime. Because every V and H prime is fixed by everything in H. Therefore, H is contained in H. So in other words, doing this operation, it takes, you start with L, which is a field, it gets you a group when you prime it, and then you're back to a field when you double prime it, and you've got a little bit bigger, right? Same with the groups. If you start with H, you prime it, you're in the field, you prime it again, you're back to a group, you've got a little bit bigger, potentially. No, and that's a good question. You know, there's a containment. What's interesting is that you stabilize, right, at one principle. Even though L itself, you might get bigger. And in the case that we're going to focus most on, you actually get inequality here too. But potentially you can get bigger here. But with the primes, the single primes, when you double prime the primes, it doesn't get any bigger. So let's look at why F is true. So right, because remember now, L prime is playing the role of H now. H is contained in H double prime. Right? But also, L is contained in L double prime, E. So prime again, I'm using prime as a verb here. And apply which one? So I'm going to start with the fields here, C. So L double prime is contained in L prime. Therefore, right, this is a little bit of magic, right? Because this one by part E gets you that L prime is contained in L triple prime. And then making this observation and priming again reverses the order of the inclusion. And so now you got L triple prime contained in L prime. So you get equality. And it's the same bit for, it's exactly the same for the other part. That is to say, if by E, we have H prime is contained in H prime double prime. And that's by the first part of A, because you have field containing field double prime. Also, H is contained in H double prime, so you prime again. And again, this reverses the inclusion. There's lots of operations like this in mathematics that stabilize after two steps, or after one step, it'll stabilize after two. Okay. It's probably worth mentioning here that note is Galois over K if and only if K is equal to its double prime. And more generally, if you have this here, then F is Galois over E. Only if E is equal to this. So if you just take that apart and look at the definition of what it means to be Galois, you'll see that that's true. Okay, any questions on that? Okay, so in light of this, and in light of the question you asked, right? You said, well, you know, is this always strict, or can it sometimes be equal? It's actually very important when it's equal. So, because notice you go from field to group, back to field, group to field, back to group. When is this the same? And it's actually very important when it's the same. And we have a special word for it. Let me say this generally. If X is a subgroup of the Galois group or an intermediate extension, so X is a subgroup of Galois group, okay, or is an intermediate extension. So I'm using the variable X to denote either a group or a field, depending on what my needs are. We say closed. Yeah. If X is equal, it's a double prime. Notice that if you have something that's closed, by the previous theorem, if an object X is closed, then every prime after that is closed, right? Because once you start with X, if it's equal to its double prime, we already automatically get, you can just keep going here, and they're all closed after that. Let me point out that, oh goodness, yes, thank you. This is a good place to quit at this definition. I'll leave a mark next time and we'll keep going. Any questions on that? Questions? All right, don't forget, I've got to do some things. I won't be back in my office till about noon. So if you got any questions, just and if that screws up your life, let me know and I'll reschedule something else. Other than that, I'll see you all on Friday.